Hello, everybody, and welcome to the Australian Space Discovery Centre's digital Q&A with a space expert. We're very excited to have you here today, especially for this topic. It's a really exciting one about lunar habitation, and we hope that you're fascinated by it and learn quite a lot. Before we start today, I do want to acknowledge that we're hosting this meeting here on the lands of the Kaurna people, and we pay our respect to their elders past, present and emerging. We also acknowledge their connection to the land and sky. They've been using the stars for things like navigation for thousands of years, and we know that there's a lot that we can draw from that meeting, that connection and their knowledge. And so today you are joining us to discuss the topic of lunar habitation, and we're very fortunate we actually have two space experts joining us today who are going to share their knowledge with us about this topic. The first is Associate Professor John Culton. John is the Director of the Andy Thomas Centre for Space Resources at the University of Adelaide, and he came to that university in 2019 following a career in the United States as a diplomat, as well as in the US Air Force as an officer and a pilot. And he's been researching promoting space resource sector since 2011. John also just recently finished with the Australian Rover Challenge, which was a lot of fun and great excitement. And I'm sure that he will tell us a little bit more about that. So John, I'll pass over to you. I'll just stop sharing my screen and take it away.
Great, thanks so much, Nate. Very much appreciate it. And hello to all of our school colleagues out there who are interested in lunar habitation. So I will put up some slides that hopefully will look a bit entertaining.
And we can see them. Oh, it's just switched to your desktop. There we go. We've got them back again now, John. So
did you? Okay. All right, great. So you can see these astronauts with the Australian gold and green colors on the screen there?
Yes, we can. Yes.
Yeah, fantastic. Okay. Okay, so as Nate said, my name is John Culton. I'm the director of the Andy Thomas Centre for Space Resources at the University of Adelaide. And our mission at this center is to support human beings that go into deep space and stay there for a long time. So some of you might know about the Apollo missions that happened in the 1960s and 1970s. And those missions were sometimes only 1, 2, or 3 days long. But now NASA, under the Artemis program, wants to go back to the moon, but they want to keep humans there for weeks and months at a time. And then they want to go to Mars, in which case we might be keeping humans there for years at a time. So in order for us to do that, we need to learn how to live and work in space, and we need to learn how to use the resources that we find in space to keep our astronauts alive. So that's what we do here at this center, and that involves lots and lots of really smart people, not just scientists, not just engineers, but psychologists and architects and lawyers and business people, and they're all involved in this operation. So this picture on the screen is a University of Adelaide picture showing the kinds of things that we are actually global experts at here in Australia and here in South Australia and here at the University of Adelaide, with using the materials we find on the moon to make habitation facilities for our astronauts. But I want to just very quickly go through a couple of developments that you should be very excited about, being a 5th and 6th grader, because things are really getting exciting in space. And so we're going to talk about some of those right now and where that's headed in your lifetime. So you should see a rocket landing on a landing pad there. So this is a Falcon 9 rocket, and this was a pretty amazing thing that happened back in 2015. But then only a couple years later, we had 2 of them landing at the same time. But that same company is now building a really, really big rocket ship that can carry 100 people at a time. Because if you want to build a city on the moon or on Mars, you can't take people there 2 and 3 people at a time. You have to take 100 people at a time, or 1,000 people at a time. So they're building larger rocket ships. So this is just the nose cone of that big rocket ship, and here's an astronaut down on the ground. And they're testing these things all the time in the United States and other places around the world. Multiple companies are testing large vehicles. Sometimes the vehicles blow up. Sometimes they mean for them to blow up. Sometimes they don't. But if you like to be an engineer, you're going to actually get to build things and then intentionally blow them up so that you understand how to make it better the next time. So this is one of the early test vehicles that SpaceX was launching. And we'll just take a look at this real quick. But it doesn't even have a nose cone on it. So they were just testing to see if their motors worked and to make sure they could get this thing off the ground. But then they had a much nicer version that they tested about a year or 2 later. And we'll just take a look at a little bit of this video, because this is really, really interesting. So the rocket takes off and goes up to about 10 or 12 kilometers above the ground. And then it flips over on its side. So this big, huge rocket ship that can carry 100 people flips over on its side, and that's how it gets back down to the ground, nice and slow. And once again, this is an experimental rocket. There's no people on it. They're just doing some tests. But we'll go ahead and watch the fun part at the end here when it lands. So even though it falls on its side, when it's time to land, it sits itself back up. So it's straight up and down. And then it tries to make a landing on its landing legs. But this was the first version of this rocket ship that actually flew. So once again, it's experimental, and sometimes they don't always work out exactly as you want it. So it was a really successful test, but now they're building more. And other companies are building rockets and learning to fly and land those. And then you even have space tourism. So Virgin Galactic and Blue Origin also have rockets that people can buy a ticket on that will take them up to space and then bring them back down to the surface of the Earth safely. More rocket tests are happening. So this is an escape system for a human-rated spacecraft that takes you up to the space station. So this would be the SpaceX version of that spacecraft that takes you to the space station. And then, of course, so probably most of you know that we do have a space station. It's called the International Space Station, or the ISS. That's a government-run space station, and it's getting pretty old. But there's a new piece being added on to the space station by this company called Axiom Space. And when the old government space station gets too old to stay in space, this new space station will detach and become a brand new commercially operated space station. But we're also going farther than that. We also are building space stations around the moon. So this one's called the Lunar Gateway, and we're actually constructing this right now. So we'll have another space station circling the moon. And from that space station, we'll be able to gain access to the lunar surface so that we can start building bases and stations and maybe even one day cities on the moon. I like that they have a little car here. NASA's actually building some cars. So NASA's building this car for the Artemis program. So the astronauts have to wear a suit when they drive this car. But our friends in Japan are building this car, which is pretty cool, I think. So in this car, you can actually be in a t-shirt and shorts and drive around on the moon for a couple of weeks, which is pretty cool. And then eventually, this is what a city on Mars might look like. But before we go to Mars, we're going to practice by going to the moon. And the first place we're going to go on the moon is the lunar South Pole, because we think there's a lot of water there. So water is really good for astronauts to drink, but water is also made out of hydrogen and oxygen. And if you take the water and you break it into hydrogen and oxygen, that's a fantastic fuel source. And of course, the humans can breathe the oxygen. So water is really, really important in space. And it looks like the lunar South Pole has a lot of it. So we're going to go there first. But the lunar South Pole is a pretty harsh place. So it's pretty cold and it's pretty dark. So we're going to need to learn new techniques and develop new technologies if we want to live and work there for long periods of time. So this is actually a picture of the lunar South Pole. The South Pole of the moon is right here. And this is called Shackleton Crater. And this is one of the places that NASA is looking at going first. But how big is Shackleton Crater? This is the size of the city of Adelaide, right here in the middle, about 20 kilometers around. So if you live in Glenelg, you'd be about here, and Mount Lofty is up here. So that's how big Shackleton Crater is, right here at the lunar South Pole. So these are just a few pictures of the kinds of things that might be, our interpretation of what the very first lunar base might start to look like. Is some of these things. And you can see in all of these pictures, there's robots and there's people working together. So we believe that that's going to be the most efficient and the best way to operate in the future, is that humans and robots will be working together on the surface of the moon to make all of these things a reality. When what I really like about this particular picture is that we have roads going off around the corner of this ridge and here and on both sides of this picture, going off to where? You guys are going to be the ones to figure that out, because there'll be lots of places to go on the moon and you'll be building the roads and building those destinations. So I'm talking to you right now from the Mission Control Facility at the University of Adelaide, where we can actually control rovers all around the world and hopefully soon also on the moon. We've just opened a brand new lab where we can test our rovers and we can test all of our devices in actual lunar and Martian surface conditions with lunar and Martian dirt. Here at this university, or now in Australia, we have the Australian Rover Challenge, where university students who not very long ago were sitting in your chairs are building rovers and competing on a lunar surface that we make here at the University of Adelaide. And so you can see some of their cool rovers right here in the front of this picture, and all these awesome teams of young engineers and scientists and other disciplines have been competing in that particular challenge, and it's a lot of fun. So that is my presentation. I'm happy to take questions or turn it over to Monika, because she can actually tell you how you're gonna design things for the lunar surface, which is pretty exciting.
That was fantastic, John. And I personally get so excited when I see all of that imagery that you put up on the screen. And it's actually a really good point that you mentioned other disciplines when you were talking about the Australian Rover Challenge, because space isn't just engineering, it's not just STEM. There are a range of different ways that you can become a space expert in other disciplines, such as medicine, or if you want to look at environmental science, even to understand, environmental impacts here on Earth from space activities, psychology. There's a whole range of things that you can look at. But that was a wonderful presentation. It gave us a great overview. And I think what we might do now is actually jump into Monika's presentation. And then we'll do our Q&A at the end. So our next guest is Monika Stankiewicz, and Monika is a transitioning PhD student in space architecture, focusing on lunar construction using 3D printed bricks. Now, Monika just graduated from her master's in architecture, in which she actually won an award for her lunar design, which was absolutely fantastic. Now, she previously also has worked in the space industry as part of Neumann Space, where she was helping developing satellite propulsion systems. But now she's currently working as a self-employed person at Zaphyr Design, where she provides architectural services. So Monika, welcome. The floor is yours if you'd like to share your screen and tell us all about lunar habitation and space architecture.
Absolutely. Thank you very much for that lovely intro, Nate. All right, so firstly, welcome to all our future lunar problem solvers from Elizabeth Vale Primary School. I haven't been there, but I'm sure it's very lovely. Anyway, first things first, what we're going to do is we're going to start with what is space architecture. Now, if you're like me and you didn't really know that space architecture existed as a field until a couple of years ago, well, then these next couple of slides might be useful for you. So, space architecture is the theory and practice of designing and building inhabited environments in outer space, or, in other words, creating, so designing, building, places, so they could be bases, hotels, homes, stations, villages in space, so you could have places on the moon, on Mars, or just in outer space or around Earth, for people specifically. So space architecture, not so much for the robots, more keeping our astronauts, our tourists, our settlers happy and healthy. Now, another question is, what does space architecture look like? If I say space architecture, you're automatically going to imagine a whole variety of different scenarios. But let's have a look at what other people have imagined first. So you could have an environment inside a torus habitat, which is basically a giant spinning donut. And as you can see, in this image, if you create an architecture like this, then you need to spin in order to maintain Earth's gravity inside the station. But what that also does is it changes how your architecture looks and feels. So if you look at this, that isn't necessarily the view that you would expect looking out of your window or looking out from the Adelaide Hills. And when I mentioned giant spinning donut, this is kind of what it would look like from the outside.
Monika, just to interrupt you for a quick second,
yep.
Our slides aren't updating on our side. So I don't know if you can check if you're in presentation view. Otherwise, I can share them from my end.
I am in presentation view, but it might have gotten confused. Just give me one moment to try resharing. Let's go with my entire screen. So, and then, okay. Let's try that again. So then, all right, so you can see that one there.
Yeah, we can see that now.
Yep, I think the issue is when I go to a presentation mode, it straight away wants to use both screens.
How about we do this? How about I share it on your behalf?
Absolutely.
And you can just tell me when you'd like to advance to the next slide.
No worries.
Okay, you should be able to see that now.
Yeah, I can see it. So in that case, you'll need to skip through the definition of space architecture that I just went through.
Sure.
You'll be able to see it there. Pretty straightforward. And we'll move to the giant curvy slide. So that one, that's what the inside of a space torus might look like. This was an artist that actually put together this rendering. And now you can actually see what I mean when the ground actually curves up, and it would look very different to what you might expect. Next slide, please. And then in the next slide, this is what I meant by the giant metal spinning donut. So I'm not sure if you guys have been to Krispy Kremes or eaten any other donuts. This one's a bit thin, so it looks actually more like a bike wheel. Right, next slide. Okay, so in this one is a very, very far future concept, but here it really shows how strong the imagination is. And it actually really makes us question, okay, what would a city in space look like if you have it on a spaceship? As you can see here, it's got a protective shield that's actually protecting it from the rest of the galaxy, but that shield is transparent. So something that might not be the most viable now, but if you find this really interesting, I'm sure you can invent something like this someday. Right, next slide, please. And this shows the view from inside some space architecture. So looking back at the Earth, or perhaps another planet, here it looks a lot like what you would expect in a hotel at home, but of course with a completely different view. So next slide.
That is a new definition to a room with a view.
It really is. Like, can you imagine looking out going, oh, I can see my house down there. Oh, it looks like, well, with a bit of a telescope. And then you can see that a storm's coming. So you let your mum and dad know that they need to close the windows. Anyway, so, well, something like that could theoretically be possible if we decide to make it so. Right. So on to this particular slide. So this one, some of your parents might recognize where this is from. But this is actually from a series called Star Wars, and this is a piece of concept art. One of the things that you can see there is that the actual building there has what look like very, very heavy, thick walls. And so that means that they are concerned about their protection in relation to the environment. Perhaps they get a couple of sandstorms. And they also have a lot of roofs, and the windows are relatively small. So something like that is where the designer has responded to the environment and gone, okay, there's a lot of sun, so we'll make sure that there's a big roof. The outside world is a little bit dangerous, but we want to be able to see it, so we've put in small windows. And so it's created a very defensive sort of architecture as compared to a glass skyscraper that we might see on Earth. Next slide, please. All right, now some of you might also recognize this one. So here on the right, we have the Death Star. On the left, we have a Alderaan. Now, something like this, it's hard to grasp exactly how big this is. But that's because at the moment, we're concerned with building smaller things for maybe a couple of people. But down the track, we could absolutely build a giant mega space station that has a couple of thousand people on there. Hopefully for a bit of a nicer purpose than what Lord Vader was attempting to do here. But it shows you that if we can imagine something, we can at the very least start working towards making something like that. Right, next slide, please. And of course, the inside of the Death Star. So here we've got a little docking bay for the Death Star space station. And we've got a ship there. Well, compared to John's slides, where he showed you the ISS and you would have seen things docking onto the outside, here in the future, someone has imagined that we don't need glass because we've got a force field that keeps the atmosphere in and the vacuum out, and that spaceships are able to pass through that. Now, at the moment, whilst we don't really have force fields working like this, NASA has been working on a way to electrostatically repel the dust off of astronaut spacesuits when they come into, for example, a lunar base. So whilst it's not quite a force field, we're actually on our way to making things that are like a force field and help to repel some of the dangers of a lunar environment. Next slide, please. And of course, the space station. I think you're a little bit familiar with this by virtue of John's slides. But here you can see they've got massive solar panels to take advantage of the sheer amount of free energy available from the sun. And if we move on to the next one, this is what the inside of the space station looks like. So sometimes space architecture looks like your hair doing crazy things whilst you're trying to use an instrument, because not only do we have to design differently for the environment, we also have to accommodate for the fact that the way our bodies move and act changes as well. And so that's something that would need to incorporate into our designs if we're trying to create a holistic design that keeps people happy. Next slide, please. All right, and now starting to bring it closer to what I'll be focusing on today, space architecture can also look like a little base on the moon. So here you can see what look like inflatable shell structures, which look like they'd be very comfortable to jump onto or bounce off of. But you can also see that there are robots using bricks to build a protective shell around the bases. Now, the reason for why that protective shell would be useful, I'll get into a little bit later, but this gives you another idea of what an early outpost would look like. And it also looks at the fact that, some of these shelters are open because they're designed for the robots to repair the robots as opposed to designed for humans. So already in our architecture or in our base design, we're designing for the needs of different elements or different entities within our design. Next slide, please. Right, and finally, before we launch into the challenges of designing in the space environment, sometimes space architecture looks like a base that has many connected modules, because if you look at the modules on there, what happens if you suddenly can't use one of them? Like, unlike the fire escape drills that you might have to have done at school, here you can't really go outside to the assembly field and just wait for your teacher to mark off your names. Here you deal with a more challenging situation where you potentially have to move to another module or even evacuate the base. And you can see in a giant fan all of the solar panels on there. Because again, we can't, as humans, we need energy to exist and we need energy to support our existence. Right, next slide, please. So how can we design our base for the moon? So we'll get into that, but first things first, next slide. We need to look at the challenges. So when we're designing for an environment that isn't on Earth, it has, potentially a lot of dangers. It doesn't necessarily have a lot of building materials. It's very expensive to get stuff over there from Earth. It has things like micrometeorites, or if you've got a rocket that's launched right next to your base, it might have kicked off a bunch of rocks directly into your window or into your habitats, which wouldn't be very nice. It doesn't really have a lot of space tradies, because at the moment those are quite expensive, and it has a lot of radiation, so you don't have as much protection from the sun because we don't have an atmosphere. And because we don't have an atmosphere, we don't have air to breathe. So all of these things make it really, really fun to try and solve these problems and come up with an interesting solution. But I'll get into these challenges in a little bit. Next slide. So to summarize all the challenges, it is very dangerous up there. When we're designing, it is life or death for the people that are inside the base. But that is part of what makes it so cool. When you're out there and you're just trying to solve a problem, so maybe you do want to design a force field, you know that your force field is directly helping someone out there do something that humanity has never, ever, ever done before. Next slide, please. So what you might have noticed from the examples of space architecture that I've shown you so far is that they all looked quite different. And the reason why is because they all responded in different ways to the surrounding environments. So one of the things that you'll notice is that, for example, a beach house here in Adelaide will have a slightly different architecture to perhaps some of the buildings in the middle of the city. The beach houses tend to have big windows, all facing the ocean, whereas the buildings in the city might have a lot less space and be squished up or be crammed into skyscrapers. So the environment, to some extent, dictates what solutions we can and can't use within our architecture. Next slide. Now, first things first, when we look at the first challenge, imagine you've landed on the moon. You've got your spacecraft nearby and you've managed to land it, not crash it specifically, and you look at what can you build with here? There isn't really a lot. So if we move on to the next slide, we can look at what there is available and try and use the things that are on the moon. So what you noticed in that previous picture, hopefully, is that there is a lot of lunar regolith, so a lot of lunar dirt. We can actually mine that dirt, extract materials, use it to build bricks or use it to 3D print other things, or we could get other elements like titanium, or we could get some silica out of there and try and print some other things. So our materials there that are free and easy to use, well, I say free, we have to do a bit of work to get there. But the main point there is there isn't any wood, there isn't a Bunnings. You can't really go down the street and just pick up some tools or pick up whatever you need, because whatever you need is very far away. Now, as John mentioned, there is ice and water at the North and South poles. So we could, potentially use that as a building material, but we would also want to use that ice for our explorers to keep them happy and healthy, and also potentially for fuel to support other missions to Mars. So these are all things that you need to weigh up and consider when you're designing your base. So the question here is, what would you build your base with? Would you try to use the dirt, or would you try to import stuff from Earth? It's always a bit of a balancing act. Next slide, please. And on to our next problem. What you'll notice is that on the right, you'll see Earth. On the left, you'll see the moon. Now, If you're not too sure about how far away that is, imagine you're traveling for 3 days straight just to get to one place, and you can't stop at a servo along the way. That means it's very, very far. If you look at the Earth and you see the country and you see a speck on that screen, you are maybe a tiny fragment of that speck on the screen. You're very, very small, and that is very, very far. And the challenge that that presents to us is the cost in getting things from Earth to the moon. Next slide, please.
It's like a really long trip to Bunnings, but Bunnings is closed and there's no sausage sizzle when you arrive.
There's no sausage sizzle, no, unless you bring your own. So some of the ways that other people have been trying to solve the problem of moving things from Earth into space is by creating architecture that collapses or folds out or is inflatable. So what you'll notice is that on the ISS, they experimented with one particular inflatable module to see how that would go in a space environment. And whilst that would absolutely work in terms of creating a space that is good for the people inside, one of the issues there is that that dust that I showed you that's everywhere, it is razor sharp, so sharp. Imagine going to the beach, but instead of sand, you've got needles everywhere sticking into you. Now, if you've ever seen what a needle does to a balloon, we don't want that happening to our habitats. But we'll look at that a little bit more later on. One of the things you can see here is that someone's come up with this concept where they've got this tunnel and they're actually folding it out. So if you're a little bit clever and you like folding things, you could create a base that starts very, very small, like the one at the bottom, and then expands up or expands out. So how could you design your base so that we have as few materials as possible from Earth? Would you go with a folding solution? Would you try to use perhaps the materials that we have there? That solution is up to you. Next slide, please. On to our next problem. Let's just say you've built this really cool and awesome base. You've managed to use the materials from the moon, so perhaps some of the regolith. You've managed to use something that was very collapsible, and you're on the moon, you're set up, you're happy. Then suddenly, boom, you've got a meteorite or you've got some debris that smashes into your base, creates a big hole, and you can't really send out the tradies down the bottom to fix it. How do we design for something like that? Next slide. Some solutions that other people have looked at is, for example, building a very, very thick shield. So you can see the metal there where it's actually had about half of it dug out from an impact that simulates a meteorite impact. And you can see next to it these very, very thin slotted pieces in a square, which is where NASA was looking at Whipple shields, or something called a Whipple shield. The way it works is that you have very thin pieces of metal. The debris comes in, hits the first one, scatters, and then stops on the second one. But as you can see in the other pictures here, at the moment, some people are experimenting with just covering their base in a really, really thick shell of regolith or dirt. Other people are looking at 3D printing particular walls, or perhaps designing their bases so that they have all of the panels at an angle so it has a higher chance of bouncing off any of the debris or meteorites, much like in tank armor. So, as you can see, this, as we expand onto the moon, this is a pretty critical issue over time. And one of the other issues that's related to this, if your base gets hit, how do you fix it? If you've only got one robot arm that goes around and prints continuously, that robot arm might be great at printing from the top down, as you can see in the bottom right picture, but it might not be so great at printing at an angle. Might have a couple of issues. Next slide, please. So here we have a very handy astronaut with a drill and a torch, and this starts bringing home the next slide, which is all about our builders. So as John would have mentioned, we're more likely to have a combined robotic human workforce on the moon, but one of the questions there is, what robots do we use? Do we use different robots to find minerals, like the Viper one that's to the right of my little handy tradie man with a plank? Do we use robots to print our bricks? Do we use our robots to climb our structures and print as it builds? Or do we use one big robot that prints from the ground up, and then we're limited by how much or how far that robot can reach? Or do we use a different robot to make our roads so that other robots can travel further? these are all questions that we still need to answer because nobody has really come up with the best possible robot for the solution. People are still trying to solve this problem now. And the reason why we like robots is because they don't need to breathe air. They're a bit easier to fix with spare parts. We can't really put a spare arm onto someone. That's not really how our medicine works at the moment. And it means that if there is that razor-sharp lunar dust, it's not affecting our people as much. The robots instead have to deal with it, and they can be built a lot tougher. So here's a bit of an open question for the students here. How could the robots and humans work together on your base? What would that relationship look like? Would you have like a dog pen or a robot pen where you go and your robots sit there specifically and sleep overnight or recharge? Or would you have your humans riding the robots to different places? So here, it's a bit of a tricky question because robots can theoretically do whatever we want them to, but in order to do that, we need to imagine what they need to do first. So there's a lot of abstract thinking there that needs to go on. Next slide, please. And on to our next challenge. On the left, you have the sun. On the bottom right, you have a supernova. What both of these are producing are radiation. Now, unlike the Earth in the middle here, we don't have a magnetosphere or as much of one on the moon. We don't have a lot of protection on the moon against this radiation, which means that suddenly you've now got people who can get very sick if they get exposed to too much radiation. And unfortunately, we don't have any space-grade sunscreen at the moment that can block it all completely. So if we move on to our next slide, how could we potentially deal with this particular problem? So again, this looks at our architecture. We could, for example, bury our base in dirt or print a solid shell that's, a bit thinner and potentially more or less easy to repair. Or we could cover our habitats in ice. And that's where that trade-off happens. Do you want to use the ice for your habitat, or do you want to use the ice for the people inside the habitat? Or, if you didn't know this already, the moon has lava tubes. Do you instead perhaps be a little bit lazy and go down into the lava tubes and build your bases there so that you don't need to build your own radiation protection? Or do you instead dig down and into the base, like you can see in the bottom right? All of these different decisions means that your bases and your architecture will look completely different. So how could you shield against radiation? That's up to you. I've got a couple of solutions there. Next slide, please. Our next challenge. Here, we can see the moon in the top left, Earth in the bottom. Now, the Earth has this particular blue shimmer. And as you can see, the moon doesn't really have that. So that shimmer indicates our atmosphere, or the air that we can breathe, as well as some of the protection from radiation and from, the vacuum. And then on the moon, it's a very stark, clear image. We don't have that atmosphere. So next slide, please. What that means is we now have to design so that all of the air stays inside our base, and if anything breaks, we can fix it relatively easily. So what I've put here is a couple of different ideas and a couple of different potential solutions. So Foster and Partners, what you can see in their little hut in the top left is that they have an airlock. They have a passage connecting the outside to the inside. And inside that passage, they've got a couple of different modules. So that's one way you can control the ingress and egress of people going in and out of the base, as well as control the potential for losing any air by saving as much of it as possible. But if we look at inflatables as a solution, what would those inflatables look like? So in the top right-hand corner, you've got the two little pods, which look a bit dirty because they've gone through a lot of testing. Or you could go a little bit more crazy and cool and abstract, and you could go for the bubbly, inflatey figure in the middle. Because at the end of the day, when we create a base, we're going to need to create a series of spaces that connect together. And that is one potential way of doing so. Or again, if you feel like it, because this is all up to the scope of your imaginations, you could create this inflatable structure and then you could hide lights inside it so you can create different effects inside your base. You could tell people when it's time for bedtime by dimming all of the lights in the sleeping module and then waking them up in the morning. Or if you're particularly clever, in the bottom right, you'll see that I put a giant stone cavern down there. If we dig underneath and we try perhaps melting some of the bricks together, we could create like this ancient temple-like structure that is completely sealed off from the outside environment. At the end of the day, we effectively need to make a bubble for our people to live in. So how could you create a safe environment inside your base? Next slide, please. Now, we've gone through designing our base to deal with the environment and how that would affect the overall look and feel of the architecture. But the next question is, how can we design our base for people? Next slide, please. So we need to keep them healthy, and that means both mentally and physically, because if you're sad on a space base, you're not going to have a great time. And so we need to find ways to make people or help people enjoy their time up there. Next slide, please.
Monika, just very quickly, I'd like to just draw your attention for time. We are running short, so we'll probably run over the session time, but if we could just be mindful of that as well as we move forward. Thank you.
In that case, I'll do a quick 30 seconds per slide, if that. Challenge 1, sleeping. People in the 17th century on pirate ships have used hammocks to sleep in. Other people on the ISS strap themselves into sleeping bags. People on airplanes create little pods. What would your sleeping area look like? How can you get away from everybody else and have a bit of a private space? Next slide. Challenge 2, exercise. If you can jump and 3 meters high on the moon and stay there for about 6 seconds, how does that change the rules of basketball? How do you make your weights heavier so that they can keep people healthy? What new types of exercise could you introduce? Next slide, please. Next challenge, eating. At the moment, everything gets sent in packets, but people have also been playing around with the idea of 3D printing different types of food, like pizza, growing plants in space and creating green rooms so that are nice and relaxing, or even using crickets and turning them into flour that's high in protein so you don't need to bring cows to the moon. Next slide, please. Fun. And this is one of the major challenges. If you get bored on the space base, you're prone to getting very, very silly. So what new ways of playing could we introduce, or what new games could we introduce? Would we have people on the moon playing with people down on Earth? Would we introduce rover racing? Could one of you maybe work out how to make a swimming pool on the moon? Or could you maybe make a giant 3D sculpture in sculptural space and float around it and change different angles? That's completely up to you. Next slide, please. But ultimately, we really need to come to who will help us make an amazing space place or an amazing space base. And you've got doctors, you've got engineers, you've got psychologists, you've got artists who help people imagine what could be possible. You've got engineers that help make that happen. You have people like John who help build a community and bring it together. You have people like Nate who help spread the education to a bunch of people so that they can actually maybe have an idea of what's possible. So who else can help us make an amazing place? Next slide, please. That would be you. Every single one of you watching this right now is capable of making an amazing impact on the state of the world that we have today, and even in the state of space. Next slide, please. So what that means, no matter what sort of problems you like solving, maybe you like writing, maybe you like math, maybe you like making cool images, maybe you like making video games, maybe you like engineering. It doesn't really matter what you're interested in. All of those things can help us in space and help us advance as a human race. So if you love space, you can find a way to help. I believe that each and every single one of you has the power and the ability to make change. Even if you don't believe in yourself, I do. So in ending, I'd like to say ad astra per aspera, or through perseverance to the stars. Thank you.
Excellent. That was great. And yeah, I echo what you're saying about each and every individual being able to make a contribution and make that, a fantastic future for us all in space. A colleague of mine, Liam, he reminisces about when he was in university, one of his university professors told him that if he has an idea and, regardless of whether he thinks it's a good or a bad idea, to cling to it because it could be the first idea that anybody has ever had, the first idea of its kind. So, and I think that's true. So if you're interested in space, definitely I echo what you're saying, Monika. Thank you very much for your presentation. That was brilliant. I think what we'll do now is we will invite Mr. Jenkinson and Mr. Jenkinson's class to join us. Hello, everybody.
Hello.
Can you hear us all right?
We can hear you, yes.
First of all, thank you very much, Monika and John and Nate, for organising that. It was very informative. and really right on the money of the things that we've been talking about. So Monica and John, I'm not sure if it was passed on, but we've been undergoing a project about developing a moon base through the ESA, the European Space Agency, using Tinkercad. So they've had to do a bit of research around the conditions on the moon and what they need in their moon camp to justify why they've done what they've done. So a lot of what you said was really hit the mark in terms of what you were talking about. So what we might do is we'll open it up to the students. They've come up with some really interesting questions that they'd like to ask you, and whoever feels confident in answering that question can just jump in. So who'd like to start with one? Mike? Big loud voice.
That's the best. Seeing all of those hands in the air.
Big.
What are some things for lunar housing we should put in consideration?
Did you hear that?
If you could repeat that back to us, that would be great.
It was, what are some things in lunar housing that they should include for their consideration? Was that correct?
Yes. Yep.
So one quick thing, unless John wants to quickly jump in. So when you go, one thing that you have in your house is you have a bathroom. Now, one of the things that people have tried to solve is how do you poop in space? And so that would actually be a very important consideration for the moon as well. Because if you get it wrong, it can just sort of float away. And you don't want that, do you?
It's a messy situation.
It is a very messy situation. So you could look at bathrooms in space, as well as would you have a pet there? And how could you look after your pet?
Okay, we might have another question. Caleb.
For the Japanese car that John was talking about, would it have an extra amount of fuel to other cars?
I'm sorry, I didn't hear the end of the question.
He said, so the car that was designed by the Japanese car, sorry, would it have to have an extra amount of fuel, or even what kind of fuel source would it have?
Probably it's going to be electric, right? So we have electric vehicles here, and if you go and look at a picture of that vehicle online, you'll see that most of the pictures show there's a big tube on the side. That tube is actually a solar panel that can be unrolled so that the vehicle can recharge.
All right, Kobe.
What are the spacesuits made out of?
Was that what material a spacesuit's made out of?
That's correct, yes.
Let's see.
Go ahead, Monica.
So, right. So a spacesuit is made out of several layers of fabric that are sewn together. And when the first spacesuits were introduced, they had to get little old grandmas who were really, really good at sewing and would, for example, sew underwear to work together on these spacesuits so that they could be stitched together perfectly. And spacesuits are also white on the moon to reflect as much radiation as possible to try and keep the people as safe as we can make them. So I don't know exactly which type of fabric, but that gives you a little bit of an idea of how they're made and what they're made out of.
Aaron?
What type of electricity do you use for the moon?
Oh, this may be more towards maybe how you're generating it, I think.
Yeah. So how would you generate electricity on the moon? Or what do you think would be the best way to generate electricity when on the moon?
So John, would you like this one or shall I?
Well, I can start off. Initially, it's going to be solar panels. So, solar panels that aren't too much different than probably the ones that are on your parents' house or in your neighborhood. But the moon and the Earth are close enough to the sun that you can actually generate quite a bit of electrical power off of a solar panel. So, at least initially, that's probably going to be the first thing that we'll use. Once you get to Mars or get a little bit past Mars, you're so far away from the sun, solar panels begin to lose their effectiveness. But while you're on the moon, that's probably a good thing to start with. If you're on the lunar South Pole, though, you may not have sunlight all the time. So you'll have to have big batteries or some other way of maintaining electrical power during some long lunar nights.
Okay, Connor?
to know if tech works, would you send it to astronauts for them to test?
Okay. So that question was to know that technology works in space. Would you send it into space with astronauts, or would you test it another way?
Was that in terms of the solar panels or
Just any
later
technology.
stage energy?
I can probably jump into this one if you like. When we're developing any type of technology, we do a lot of different tests. Spacecraft go through many different stages before we actually build what's called a flight model, which is what we send to space. And so some of the tests that we do here on ground are things like vibration tests and vacuum tests. So we're always continuously testing technology to make sure that it works and does what we want it to do. And then we keep changing the design to improve it as we go until we know that it actually works. Some things do need to be tested though in space, and there's some special space missions, so demonstrator missions, which are completed in space on orbit to demonstrate that that technology works in the environment that it's intended to work in.
Kenzie.
What type of foods can you grow on lunar soil?
Ooh,
That's great.
That's a great question. So at the moment, people are trying to find out what exactly we can grow there. And normally on Earth, what we do when we go to a new place and we want to try and work out what will grow is we build a botanic garden where we test out a whole variety of plants. So one of the things that we would need to do on the moon is design our very own botanic garden and see what works with the lunar soil. Because at the moment, whilst we might have an idea of what would grow well, we don't actually really know exactly what would grow well and what wouldn't. Now, I know that China has managed to grow a little bit of a plant on the moon, but it died pretty quickly because it wasn't protected properly. So that's something for you to try and work out for us.
Orlando.
What inspired you to become a lunar architect?
Did you hear that one?
That?
Yeah. What inspired you to become a lunar architect?
Well, mainly, so I had my architecture background and I was working at the space company and I was looking at those two things and I did a bit of research into, okay, what sort of space stuff is there with architecture? And then that's when I found out that, space architecture is a field. And then I went, oh my gosh, that's so cool. I want to do that, right? Let's focus everything on doing that. And so it was mainly, I didn't know about it before. And then I found out about it. And when I found out about it, that's what inspired me to really, really go for it and just try my best.
Ruby.
Is it possible to create artificial gravity and how?
Oh, so unless, John, would you like to answer this one? Otherwise, I have a quick response.
Yeah, go ahead. I didn't quite hear the whole question.
Okay, so one way you can generate artificial gravity is with that torus or with that donut space ship or habitat that I was showing you before. So the way that generates artificial gravity is actually by spinning the people around it. And as it spins, what you're doing is you're standing on that outside wall that's spinning a lot. I'm not sure if, Nate, you could bring up that particular slide, but that might sort of help as opposed to me trying to motion with my hands. But yeah, by spinning the people and so that you stand so that your feet are pointing outwards, that's how we can generate artificial gravity. And if you're designing a mining station, for example, you can take advantage of that and the reduced gravity towards the middle of that spinning to actually move heavier materials into a station. But at the moment, we don't have a magic switch that you can just flick and have people sit on the ground. So you can see here how all of the houses are pointing down towards the outside of the habitat. So that's where the gravity is, on the bottom there.
Okay. Unfortunately, guys, I think we might have to wrap up the questions there because Mr. Dan has to get his class back to pack up their bags and get ready for home time. But again, we thank you very much for your time and your expertise in this area. We'd love to share some of our designs with you, as I'm sure you'll see some of the knowledge that you've imparted embedded in the designs that we've done. So again, thank you very much. Everyone, guys, can you say thank you?
Thanks, guys. It was really fun
Thanks,
talking
everybody.
to you, and I can't wait to see your designs.
Thanks, guys.
See you.
Thank you very much, everybody. And please, if you do want to come and visit us sometime at the Australian Space Discovery Centre, we are open. We do take school groups as well, and we have a lot of other digital events upcoming, so we'll keep you informed about those as well. But thank you once again to John and to Monika as well for joining us today. We'll see you next time.
Thanks, guys.
See
Thanks,
ya.
Nate. Thanks so much. Cheers.
Thanks, Nate.
Bye.
Thanks, Tom.
No worries.
Thank you, Nate.
Great job, Monika.
Oh, thank you.